Good afternoon, everyone, and welcome to my talk. Today, I will discuss about shaping the future of bridge engineering, focusing on smart, resilient, and sustainable solutions. My professorship is in structural engineering with a particular focus on bridge structures. And I will share some perspectives on our research and also some challenges we face in this field. I think we can all agree that bridges are an essential part of our daily lives. But what exactly is a bridge? Simply put, a bridge is a structure built to connect people and places by spanning obstacles such as rivers, valleys, sea channels, or other barriers. Bridges are vital components of our modern highway and railway systems, often serving as crucial lifelines in a nation's infrastructure. They play a significant role in supporting transportation, driving economic growth, and also improving the quality of life for everyone. But have you ever wondered how many bridges do we have here in Finland? In Finland, there are about 15,000 road bridges and more than 2,000 railway bridges. Then what about their surface life? Or how many years do we expect them to last? Quite long, actually. Most of them are designed to last for 100 years. Then, how old are they now? Or how long has they already been in surface? This figure shows the distribution of the number of bridges by their year of completion. As you can see, most of these bridges were built after World War II, but over time, the construction of new bridges has slowed down, while the existing ones continue to age. Now, what about their condition? According to the Finnish Transport Infrastructure Agency, about 5% of road bridges are in poor condition, and also this number of such bridges is still slowly increasing. It was also estimated that by 2020, about 7,000 bridges would need renovation. So the big question is, what will happen in the next 20 or 30 years? If we look at the current trend, it's become clear that after another 20 or 30 years, most of the Finnish bridges will be over 50 years old, and some of them will be even over 100 years old. So simply put, our bridges are aging. Actually, this is not just a problem in Finland. It is happening in many other countries as well. So to some extent, it is a global issue. With this background in mind, let's now turn our attention to future challenges and opportunities in bridge engineering. First, how can we improve the management and maintenance of existing bridge structures? Especially, how can we develop better methods for fast bridge damage detection and also for bridge health assessment? Another question is, how can we improve the bridge robustness for both existing and new bridge structures? And what about sustainability? As we move toward a greener future, how can bridge engineering contribute to the green transition? While these challenges are ahead of us, they also present many opportunities to find solutions. In my group, we are working on several key research topics, such as structural health monitoring, bridge robustness, and demandable connections. Now let's start with the first topic, structural health monitoring. Bridges are designed with a long surface life, but over time, bridges or bridge components can experience degradation or damage. While regular inspections are crucial, but they may not always detect damage in time. And this is where structural health monitoring systems comes into play. These systems can help us to detect the damage at the early stage and allowing us to prepare the repairs more efficiently and avoid costly failures. Currently, most structural health monitoring systems use direct method, where sensors are installed directly on bridges. These sensors provide us valuable information and data about the bridge's condition, but since one bridge may require many sensors, so this method can be expensive and also time-consuming. As a result, these systems are typically used only for important or long-span bridges, but for short-span or medium-span bridges, the structural health monitoring systems are often not implemented. To address these challenges, my group is working on developing a vehicle-based bridge damage detection method. In this approach, instead of installing sensors directly on the bridge, we install them on the vehicle. This allows us to collect data indirectly as the vehicles travel across the bridges. Since the same sensors on one vehicle can be used to scan multiple bridges, so this method can be cheaper, faster, and safer. It also reduces the traffic disruptions as there is no need to stop or slow down the traffic. In my group, we have performed some lab tests, such as shown here. And also, we have conducted some field tests on 2 temporary bridges in Espoo to further investigate this method. Using the algorithms developed in my group, we can identify the key information of the bridges. For example, their natural frequency, a key indicator of the bridge condition. While collecting data indirectly offers many benefits, they also present a challenge in, for example, in data processing. However, the use of AI and big data showed a great potential in addressing those challenges. Also, my group is collaborating with our partners to explore the possibility of using public transportation, such as buses, to monitor the bridge conditions. Next, let's talk about bridge robustness. Structural health monitoring system can help us to detect the damage at the early stage. But beyond that, we also need our bridge to be able to avoid the disproportionate consequences in relation to its initial damage. So what does this mean? For example, what will happen if a bridge component fails? Will it lead to the partial or even global collapse of the whole bridge? And would the bridge still function? To answer these questions, we need to exercise the bridge robustness. In my group, we studied the robustness of some typical bridge structures, such as the twin girder bridge shown here. We analyzed the impact of severe artificial damage applied to one of its 2 main girders. We also have one ongoing PhD project focusing on the robustness of truss bridges. Especially, we examine the effects of different damage severity, the load transfer mechanisms, and the role of secondary members in redistributing the load after the fracture of one or more truss members. Our goal is to find effective ways to improve the robustness for both old and new bridge structures. So finally, how can bridge engineering contribute to the green transition? The construction sector plays a key role in sustainable development, and bridge engineering is no exception. There are many ways we can contribute. For example, by using structural health monitoring systems, we can enable a wiser use or even a reduced use of construction materials by improving the design. And with the research on bridge robustness, we can improve the long-term safety and reliability for our bridge structures. And all these efforts can also help to extend the surface lives for our bridge structures. Repurposing and reusing structural components at the end of a bridge's life is another way to reduce CO2 emissions. But traditional connection methods make the deconstruction challenging. Therefore, the design of the joints or connection is the key. In my group, we have one ongoing project working on developing different demountable connections. These demountable connections are designed for fast assembly and easy disassembly, and they can bring us many benefits. For example, the use of demountable connection can speed up the construction, enable faster repairs, and also allow for the easy deconstruction at the end of the bridge's life. However, reusing and repurposing bridge components remains challenging due to the concerns on the fatigue, damage, and also the difficulties in predicting their residual surface life. Still, research like this can open new possibilities for more sustainable bridge designs. To summarize, by addressing the challenges we discussed today and conducting research in these areas, we can work towards making our bridges smarter, more resilient, and more sustainable. Finally, I would like to thank my family, my team, and also my colleagues for their unwavering support. And thank you very much for your time and attention.